on the blackboard. If you don't understand, it's elliptic equation for measures and lower bounds for densities.
Okay, first of all, I would like to thank the organizers for the invitation to this institute. It's a great pleasure to be here. I was here for the first time 20 years ago when it seems that there was no. Oh, please also the rest. And it seems at that time this institute did not exist. At least the building did not exist, definitely. And it's very nice to meet here many colleagues, and I even met here some of my Moscow university teachers and also people with whom I was a student many years ago. So it's really a point of high concentration and intersection. Originally, I was planning to give a short survey on elliptic equations for measures. But then, on having arrived here, I learned of Malevic's death, and I decided to slightly change the subject and to reflect something from our last discussions with him, and to speak a little bit on the subject in which he was involved in the last years, and about which he wrote one of his last papers. And so I would like to dedicate my talk to his memory today. And actually the equation is written on the blackboard, but I should explain what does it mean and who are these letters. So throughout mu will be a probability measure on RD. So why on RD in this place where infinite dimensional stochastic equations are discussed? I'll explain a bit later why RD also appears in this situation. And now who is L? In general, this L is a second order elliptic operator. But to simplify notation, we shall consider L of a very simple type. It will be Laplacian plus first order part. So this first order part is given by a vector field B. And the equation, this short equation means just the integral identity. So it's a kind of equation in the sense of distributions. But in order this equation could make sense, of course, we need that this expression, L of f, be integrable with respect to mu. And this function is with compact support. So this is the same as to say that this B is locally mu integrable. So once we have this assumption, then the equation at least makes sense. And now a few words are in order to explain why such an assumption is reasonable if we have in mind some applications to infinite dimensional say measures or infinite dimensional diffusions. So suppose again for simplicity that we have a diffusion process in R infinity, so the countable product of the real line. And suppose that the diffusion is governed by a stochastic equation, again with a constant diffusion term, and with a drift which is given by a sequence of one-dimensional functions. So this diffusion equation is, in this specific case, is written as a countable system of one-dimensional diffusions, but of course they interact, so it's not an independent system. And suppose also that this diffusion has a stationary distribution. This means that if T is the transition semigroup of the diffusion, then we have this identity, say, for all reasonable functions phi. For example, for all bounded functions phi, which depend on finitely many variables, and say are smooth functions in these finitely many variables. Then one can show, at least under reasonable assumptions on B, of course, that it follows from this equation that you have exactly that identity. Say for functions phi which depend on finitely many variables. Say just on the first n coordinates. And this equation gives some information on the finite dimensional projections of this stationary distribution. So if you take the conditional expectations, if you consider the conditional expectations of these functions generated by the projections to Rn, then you get functions on Rn. And then it follows from this relation that we're exactly in this situation, just with Rn in place of Rd. And the situation is similar if the diffusion term is non-constant. Then we do the same with the second order part, and we get some elliptic operator. So this shows that the finite dimensional projections of the stationary distribution satisfy our elliptic equation. Observe, by the way, that the finite dimensional projection of the diffusion may not be a diffusion if there is some interrelation between the equations in this system. If it's not a sequence of independent processes, then in general the projection, the finite dimensional projection of a diffusion will not be a diffusion. And many other things will not be preserved under this projecting. However, this property to satisfy the elliptic equation in this sense will be preserved. So this shows how this situation arises, this finite dimensional problem arises when you deal even with an infinite dimensional system. And it also shows that the information which is available about this B may come through various integrability properties with respect to mu. So, for example, in the classical theory of second order equations, say for functions or measures, typically some assumptions are made on B, and typically they are related to the structure of RD. For example, typical assumptions are that B is, say, continuous or locally bounded or locally in LP or differentiable or something or locally Lipschitzian, etc. But if you obtain this finite dimensional B in this way from the conditional expectations, then you see that practically it is very difficult to ensure such properties. So for us, the most natural assumptions on B will be of the following type, that say B is globally in L1, or B is globally in LP with respect to mu, not with respect to Lebesgue measure, because no information about Lebesgue measure is available through this conditioning. But the information related to mu is available because, for example, if the original functions in this sequence were, for example, in LP with respect to the measure on the infinite dimensional space, then after conditioning, you get the same for these conditional expectations with respect to the projection of the measure mu. This explains why we also here impose assumptions like that. And now the following, yes?
Condition with respect to which measure, or
the conditioning with respect to the measure on the with respect to this stationary measure on the infinite dimensional space. Of course, we assume it exists in this example. Yes.
So, can you be more precise? Which is your measure mu? Find the measure mu obtained from this infinite dimensional measure mu.
Here there was a measure on the infinite dimensional space mu. Then we took its projection on Rn. And then this projection, or Rd to be consistent with the previous notation, its projection, its finite dimensional projection, will play the role of our basic measure in the finite dimensional case.
So is it something that you start with the Markov process in the big space?
Yes.
With invariant measure?
Yes.
And then you project the measure on small space?
Yes.
And you get another Markov process on the small space?
No, on the smaller space there is no any process. On the finite dimensional space there is only the projection of the measure.
But you can have a process generated by L.
It's a question whether it's possible. Later I'll make a remark on this, but in general it's not quite obvious that.
That was my question.
It's in general it's not quite obvious that after you get this finite dimensional operator that it produces a process. It's not quite obvious. Especially, it's not obvious whether it will produce a reasonable process, not, say, a process in the sense of Dirichlet forms, but a reasonable process governed by a stochastic equation. It is not quite clear because we shall see why. This was just an example explaining why we're talking of such a strange assumption that conditions on B are expressed not in the standard way, but rather in this maybe explicit, not explicit way, because we are looking at this equation, so in principle mu is unknown. And so the properties of B, which is explicit, we assume that B is explicitly given. So the properties of B are expressed rather implicitly in terms of this unknown solution. So this is, I would say, the main novelty with respect to the classical situation. And now we would like to get some information about mu by using this quite indirect information on B. And so the question is, which information can we obtain by using these assumptions. And it turns out that one can get some reasonable information. Okay, so now I completely delete the infinite dimensional case, and it will never appear today again. However, I would like to make another observation. Most of my talk is covered by a recent survey of the three authors, Krylov, Röckner, and I, published in the Russian Mathematical Surveys last year, in the last issue, number 6. It's a quite long paper, more than 100 pages, with many references, of course, to other authors, not only to these three authors of the survey. And there is a short chapter, an introduction to the infinite dimensional equations of this sort. And also, I will not give any references, because for those who are interested in a particular reference, everything can be found in this survey. Okay, so now I'll formulate some initial results which give some information on mu. So first of all, suppose now that B is like that, locally integrable with respect to mu. So this is really a minimal assumption under which the equation makes sense. Then it follows from this minimal assumption that mu comes with a density. So that is, mu is an absolutely continuous measure. If more is known about this B, then more can be said about this density. So suppose that B is mu integrable locally, slightly better. Well, not slightly, in fact, with P bigger than dimension. Then it follows that this density, which exists by the first assertion, is in the local Sobolev class, which consists of functions which are locally integrable and whose generalized derivative or Sobolev derivative is locally in LP with respect to Lebesgue measure. So in particular, this density is this density has a continuous version, or even locally Hölder continuous version. And it follows that now this equation, if you look at the defining expression and replace mu by this dx, then one can integrate by parts. And then this equation will be written in a bit more classical form. However, in general, unlike the classical case, this density may not be positive. And this is seen in very simple examples. So suppose we take any C infinity function, say not just a function, but a C infinity probability density. So it is non-negative. And let us take for B, let us take its logarithmic gradient. So we set it 0 on the set where the density vanishes. So if rho is positive, then it is given by this expression, and if at the points where rho vanishes, we set it 0. Then it is easily seen that the equation is fulfilled. Namely, the equation becomes this. And this holds because you integrate by parts in this term with the Laplacian, use that f is with compact support, so there is no boundary term. And this rho cancels out with this rho. And after integration by parts, you get minus, finally you get 0. This is the simplest, probably the simplest case when one can explicitly verify the equation. And in this example, you see that it may happen that B is integrable with respect to rho, with respect to this measure with density rho. And it can be integrable very well. It can be not only locally integrable, it can be globally in all LP. But still, rho may have zeros. It is known that given any closed set, you can find a probability density, say non-trivial closed set, different from the whole space. You can find a probability density whose 0 sets is exactly the given closed set. So from the point of from the viewpoint of Lebesgue measure, this B may be quite singular. Say if you take for the density something like this one, then you get only one singularity of this type at 0. But it is easy to organize a singularity on a set of positive Lebesgue measure, and a singularity which is not locally integrable with respect to Lebesgue measure. So from the classical point of view, this drift may be very singular. But for this result, there is no difference how singular it is with respect to Lebesgue measure. Once it is integrable, then it's fine. And obviously, this shows that one cannot hope to get positivity of density in this situation. And now I turn to the second part of the title of the talk, lower bounds for densities. Now, yes?
Before you continue with the second part, are there any known results for P between your D and 1?
Well, there are some results, but not of this type. For this particular statement, there are counterexamples showing that one cannot make P smaller than dimension or equal to dimension. Well, in fact, it's not quite correct. I mean that if you take only these assumptions, then it is not possible to replace this, for example, by p equal to d. But of course, it might be possible to do the same with some extra assumptions.
But in a sense, one could ask a very natural conjecture is that if you have b in LP log, whatever p is, then rho will still be in the sublet space WP1. Is it a known counterexample?
We did not analyze this problem in the case you mentioned with this very precise information that some log appears. So our counterexamples are a bit rough. They only show that if you, for example, say in dimension 2, it is not enough to put here, to replace p by 2, for example. But it's, by the way, a bit strange. One cannot say in dimension 2, it's not enough to put here 2 in place of p bigger than 2.
No, the question is what it's not possible to get Helder continuity. That's
yes,
what you say.
yes. Not only Helder continuity, but also Sobolev. There will be no Sobolev membership in this case.
But with which order Sobolev spaces?
Of the same order.
It's not possible that you have counterexamples. So.
Yes, yes. But what is strange? But what is strange? If in this result you impose the global L2 independently of dimension, then there is some Sobolev membership, and then the following integral will be finite. So this means that rho, or it's better to say that the power of the square root of rho will belong to the second Sobolev class. And so the density will have finite Fisher's information. And this is true in any dimension. But if this is given only locally, then somehow density may not be in the same Sobolev class. But of course you are right. One might ask of some other, say, fractional Sobolev classes. And there are some results in these directions, but they are a little bit technical, so I will not mention any more in this direction. So now about assumptions which would ensure that density is positive. One of the first results in this direction was obtained by Skorokhod. Long ago, I even don't remember the year, somewhere at the beginning of the 70s. So he considered this specific example. So actually, he did not consider this elliptic equation at all, but he only wanted to get a condition on this logarithmic gradient from which one could deduce that the density is almost everywhere positive. And he found a very convenient assumption. This is this one. So if remember, it is in this special situation, not of the elliptic equation, but of the logarithmic gradient. If b is exponentially integrable with respect to mu, then the density is almost everywhere positive. And also notice that this assumption is preserved by conditional expectations. So if in the infinite dimensional case, so coming back to the example where we had the infinite dimensional measure, if in the infinite dimensional case the components are exponentially integrable, then the conditional expectations of these components will be exponentially integrable with respect to the projection of the measure. So this assumption fits our framework. It is expressed in the terms which we like.
And what is mu in Skorokhod setting?
Mu, in his case, mu was just the measure with density rho. So his goal was to find a condition on a probability density from which it follows that well, of course, one might say that it's strange to look for conditions on a given probability density that it is almost everywhere positive rather than in the terms of its density itself. But in his case, he had some motivations, and he used this result to show some ergodicity and some other things. There are cases when if rho is not explicitly given, then it might be not so easy to check whether it's almost everywhere positive. And then he found this elegant assumption. Later, I would say much later, in our paper with Meyer-Wolf, we proved by using some Mozart type iterations that if this assumption holds only locally, well, in fact, for simplicity, I put this like this, but one could put here any epsilon, any positive epsilon.
So if it's true for
for some positive epsilon, then the conclusion holds. And so if one has this locally again, and again with the same b, so this is a very special case. So it is still very far from the elliptic equation. Then rho is continuous and actually strictly positive. So in fact, we showed that the logarithm of rho is continuous. So this means that not only rho is continuous, but also it is strictly positive. And as a consequence, in the situation of Skorokhod, also there are no zeros at all. At least for the continuous version of the density, there are no zeros at all. Now, that was also quite long ago, more than 10 years ago. And then some more recent progress was achieved. But I forgot to mention another important contribution due to Shoitsov and Weizsäcker. but also quite old paper, maybe also 10 years ago. They considered the one-dimensional case. So they considered the one-dimensional case. And they posed the following question. Suppose that we want, in this one-dimensional case, suppose that we want to conclude from convergence of some integral that the density is positive almost everywhere. What should we take, or what can we take for this psi? So the Skorokhod result shows that you can take exponent with some, probably with some epsilon. And they asked what are other functions psi for which such an implication holds. And surprisingly, they found a very simple answer. But assuming that psi is a convex function, of course, not for arbitrary functions, but for convex functions. So their answer is extremely surprising, and this answer is this: that this integral must diverge at infinity. So this explains how the exponent appears. So if it is exponent, then you get here an epsilon t, then this cancels 1t, and then you get a divergent integral to infinity. And actually their answer shows that you can slightly change this exponent, but practically you cannot drastically change this exponent. Their answer shows that in this Skorokhod theorem you can replace this exponent by some logarithmic factors, but you cannot really seriously change the function. And so this is also quite old, and now very recent stuff. And again, first for the one-dimensional case. Noallard, the daughter of David Noallard, published a counter-undue note a few years ago, where she proved the following bound, again in this very special case of the logarithmic gradient and the one-dimensional case. She proved the following lower estimate. So here lower estimate is this. If the exponent of this function in this, so here of course r is bigger than 1, and so she assumes that this is finite. You see that the assumption is a bit more restrictive. So now r is in power bigger than 1. So it's stronger than in the Skorokhod statement. But the statement is also much stronger. It's not only some positivity of density, but it is a quite explicit lower bound. And these two numbers depend on this integral, and probably they also depend on R. This I don't remember. Next, two other papers appeared simultaneously last year. One was the joint paper by Malieman and Nuallard. They proved the same in any dimension. Again, assuming that B is of this specific form. So again, their question was this: how, in terms of the integrability of the logarithmic gradient, to get a lower bound on the density? And it turns out that the same assumption gives this lower bound. And their proof, by the way, even the one-dimensional case, so one might think that in one dimension everything is explicitly calculated and this is an exercise. No. Even in the one-dimensional case, the proof is quite involved. And in this paper, which was published in the JFA last year, actually what they did, they reduced the general case of high dimension to dimension 1. And as you can imagine, the proof is even more involved than in the one-dimensional case. And the same year, a joint paper by Röckner, Shaposhnikov, and myself. Shaposhnikov was he's a former student of mine. A paper in Russian Comptrendu, доклады mathematics, was published, where we proved the same for any B. So not necessarily of the gradient of this specific type. So now our result applies to solutions of the elliptic equation, and it is not required that B be the logarithmic gradient. So B is just drift. And also we extended this result to the case, to the Skorokhod case, namely if this is integrable, then there is also a lower estimate, but this lower estimate is different. It is of the following type. So this is of course a very weak lower estimate, because this right-hand side decreases at infinity very rapidly, but still it is lower bound, which requires only this information. So only this information gives you some lower bound. And now the final thing. Now, of course, it is natural to address this condition suggested by Shoitsov and von Weizsäcker, and to see how is it related to our situation. And this is a very recent result, which has not been yet even published, because another student of mine was involved in this, and he was charged to do some calculations and verifications, but he travels a lot, and so at the peak time of working on the problem, he was climbing Kilimanjaro and traveling in equatorial Africa, somewhere near Somali, and so I did not dare to disturb him with such matters. But now he is back, and I hope that he will finish the necessary job, and we finally publish this. And now the final result is this. Suppose that von Weizsäcker and Schweitzow did in the one-dimensional case for the logarithmic gradient. Suppose we want to get some bound from this assumption. Technically, it's slightly different from the previous one, but this is just to simplify the answer. So at the level of ideas, it's essentially the same, just to simplify some final formulations. So suppose you have some function psi, which is convex, and we would like to derive from this condition. We would like to derive some estimate of this form. So the question is, what do we need on the part of psi, and how to find f if we are given psi? And the answer is this. So this is the final result which I wanted to mention. The answer is this. Suppose that psi satisfies this technical bound. Actually, I suspect that this is not needed, but just so far we used it in some intermediate steps. It is not restrictive. Because you saw that anyway psi in this expression can be linear, and here it says that it should not be less than, essentially, that it should not be less than logarithm. So this looks like a very weak assumption as compared to other stuff. But just at the moment, for some technical reasons, we need it. Maybe when Boris finally returns from Kilimanjaro, maybe he kills this assumption. And then we need the same as Schweitzow and von Weizsäcker. If this integral diverges at infinity, then one can find f rather explicitly. I will not show how to find f. Well, but I even can show you. F is governed, but maybe you will not like this expression. It is not very explicit, but essentially this is this one. If f is related to psi by this strange expression, in fact, by changing variables, one can rewrite this as a more reasonable ordinary differential equation. Of course, it's a question whether one can explicitly solve it, but at least it is quite explicit ordinary differential equation. So the final statement is this: if you have a convex function psi such that this strange technical assumption is fulfilled, and this principal assumption is fulfilled, then from the membership of this expression in LP, it follows that you can produce a positive function phi such that there is this estimate. And this f is more or less explicitly given. This f is not just some function. Actually, it will be a continuously differentiable function, so with some other properties. Okay, I think it's the right time to stop. Thank you for your attention.
Thank you very much. So, questions and comments? I would like to ask, in a sense, you've got, you go in a very sophisticated assumptions, etc. And could you start with some example that, say, finite dimensional diffusion process, maybe where this assumption would be important?
For constructing a process, or for what?
No, because in a sense so you want to show more or less positivity of density of invariant measure.
Yes, exactly. Yes.
So if you take finite dimensional diffusion, some finite differential stochastic differential equation with an invariant measure, would your result apply to it or not?
Yes. If we are dealing with a finite dimensional process from the very beginning, so B is given. And I skipped this part, but we also have some sufficient conditions in terms of Lyapunov functions for the existence of invariant measures. And so, in this case, once you have some invariant measure, then this second part gives lower estimates. And we also have some other results which give upper bounds on the density. And in some cases, these lower and upper bounds are of the same type. So, for example, I will not give concrete conditions, but we have some quite explicit assumptions, and I hope easy to verify explicit assumptions on B, which give, for example, the following two-sided estimates on the density. So this is not, of course, an asymptotic, because there are different, this C1 and C2 are different. But these are non-Gaussian two-sided bounds, and this alpha is quite explicit. For example, if you know the behavior of this at infinity, for example, suppose that this goes to minus infinity as x goes to plus infinity, and suppose that you know the rate, say some polynomial rate with which this goes to minus infinity, then these two-sided estimates give quite precise bounds. And say in the Gaussian case, they become really precise. But well, in no case we give asymptotics, but at least these are of, say the order is, at least in our bounds, the order is correct. And what is important, this applies to many non-Gaussian situations when this alpha may be, say any number.
Thank you very much. Other more questions? Yes.
You mentioned this recent result, which says that for general B, if this exponential function belongs to this L1, then you have some lower bound estimate for the density.
Yes.
So if we only require the positivity of this density almost everywhere, whether this local integrability for this exponential function is enough for general case?
No. If you these results show that you cannot obtain almost everywhere positivity without strict positivity. So conclusion of this is this: that if you have some assumptions related to integrability which ensure almost everywhere positivity, then actually they ensure strict positivity. So somehow it's impossible to obtain just almost everywhere positivity without automatically getting strict positivity.
Because you say that for this special case, I mean this derivative of the logarithm,
yes.
You say that the local integrability of exponential function is enough to imply the positivity of the density.
Yes.
So for general case, you don't have.
No. For general case, the same. So the last result obtained in this paper applies to the elliptic equation, not to logarithmic gradients. So this last result applies to the general case. But already this one-dimensional case shows that if you take, for example, here in this example, suppose that you take rho, which is almost everywhere positive, but has zeros, for example, 1, 0 at the origin. Then it follows from the result of already from Schultzov and Weizsäcker that you cannot get integrability. You cannot get integrability of this type with some psi. So of course there are densities which are only almost everywhere positive, but not strictly positive. But for such densities, you cannot prove that they are almost everywhere positive by using assumptions like this. So this is a conclusion. So it shows that if you are able to deduce from this almost everywhere positivity, then you automatically deduce strict positivity. So this is a partial conclusion.
Yes.
In the infinite dimensional case, when you project on this finite dimensional subspaces, how does the estimates depend on the dimension?
The estimates depend on the dimension.
But in what way?
The point is that in the derivation of these estimates, we use some Harnack type inequalities, and these Harnack type inequalities involve some constants from Sobolev embeddings, and these constants depend on dimension, and therefore all our results heavily depend on dimension. And I would like to mention that there are rather recent interesting results obtained by several authors, for example by Shirikian and several other people, who using absolutely different techniques were able to get lower bounds for finite dimensional projections, especially in the case of stationary distributions for the Navier two-dimensional Navier stocks. And they somehow surprisingly got lower estimates of measures on both infinite dimensions, estimates independent of dimension. So this is quite surprising. This is impossible to do with this our technique. But on the other hand, their case was really very, very special. I do not know of any other general results rather than this, of course, important but special case of two-dimensional stochastic Navier-Stokes.
No more questions. Thank you very much.